algebra. For today, we will discuss trivial group, monoid, and abelian group. But before we go into that, we prove the uniqueness of the identity element of a group and the uniqueness of the inverse elements of a group. The uniqueness of the uniqueness of the identity element of a group says that there is only exactly one identity element in a non-empty set under a binary operation that form a group. And to show that the identity element of a group is unique, we will assume that the group with a non-empty set under a binary operation has two identity elements. And we will show that these two identity elements are the same and equal identity element of the group. We prove that the identity element of a group is unique. This means that a group with a binary operation defined on the non-empty set has exactly one identity element. And as I said earlier, to prove that the identity element of a group is unique, we will assume that there are two identity elements in the group, and we will show that these two identity elements are the same and equal identity element. First, we let G be a non-empty set with a binary operation star defined on G. And we will take E and E sub 1 as the two identity elements in G. And we will show that E is equal to E1. For the proof, we let G under star be a group. Because G under star is a group, G is a non-empty set. That means G has at least one element. And because G is a group under star, this means that star is a binary operation on G. That means you can combine any two elements in G by the binary operation star, and the result is also in G. We let E and E1, the elements of G, be two identity elements in G. To prove that the identity element of G is unique, we show E is equal to E1. And because G is a group under the binary operation star, the elements of G under the binary operation star satisfy the three properties of a group The first property is the associative property. The second property is the existence of the identity element. And the third property is the existence of inverse element for each element in G. Because we let E be an identity element, then if we combine E by the operation star with any other element in G, the result is that element in G. We denote this any other element of G by A. Because we let E be an identity element in G, then by the second property of a group, the existence of identity element, if the identity element E is combined with any element A of G by the binary operation star, or E star A is equal to A star E equals A for every A element of G. And A here can also be the identity element E. Similarly, because we let E1 be an element of G, be an identity element, we let E1 element of G be another identity element in G. Since E1 is an identity element, it also satisfies the second property of a group, the existence of identity element, which means that if we combine E1 with any other element A of G, by the operation star, the result is that element A of G. In symbols, E1 star A is equal to A star E1 equals A for every A element of G. Now we can equate E star A with E1 star A because they are both equal to A. Or you can equate A star E equals A star E1 because they are both also equal to A. So I have used the first expression from each of these equations. We equate E star A with E1 star A because they are both equal to A. Now A here is an element of G, and G under the binary operation star is a group. And by the third property of a group, for every A element of G, there exists an inverse element denoted by A prime, also element of G. We are sure that every element of every element A of G has an inverse because G is a group and G must satisfy the third property of a group, which is the existence of inverse elements for all the elements of G. And for this element A of G, we let A prime, also element of G, be the inverse of A. And because A prime is the inverse of A, if we combine A prime with A by the binary operation star, the result is the identity element. Because E and E1 are two identity elements, we can readily equate E equals E1. We can readily equate E with E1 because they are both equal to A prime star A. The combination of the element A and its inverse by the binary operation star is equal to E. And also the combination of A prime and A, the inverse A prime of A combined by the binary operation star is equal to E1. And from these two equations, we can readily say E is equal to E1. But we will use this equation, which we derive from the property of identity elements, that E star A is equal to E1 star A. I will multiply both sides of this equation by A prime. This equation is equivalent to this equation because we combine each of this expression E star A equals E1 star A implies quantity E star A star A prime is equal to quantity E1 star A prime. We have included A prime to the left and to the right of this equation. Now, by associative property of a group, because G is a group under the binary operation star, the elements of G satisfies the associative property of a group. And by associative property of a group, the left-hand side is equal to E star quantity A star A prime. Similarly, for the right-hand side, by associative property of a group, quantity E1 star A prime is equal to E1 star quantity A star A prime. Now we can use the third property of a group for the existence of inverse elements. The inverse elements of a group have the property that if you combine A with its inverse by the binary operation star, the result is the identity element of the group. Hence here A star A prime is equal to the identity element E. For the right hand side, A star A prime The result is the identity element E1. From the left-hand side, A star A prime is equal to the identity element E. From the right-hand side, A star A prime is equal to the identity element E1. But the identity element has the property that if you combine it with any other element of the set G, including the identity element, the result is that element. Thus, E star E is equal to the identity element E. And from the right-hand side, the identity element E1 combined with the identity element with an element. Here, it's the element is the identity element itself. So, E1 star E1 is equal to the identity element E sub 1. And we have shown that E is equal to E1. And this is the end of the proof as indicated by the shaded rectangle. This equation E equals E1 tells us that the identity elements, the two identity elements E and E1 are the same and equal elements. That means that there is exactly one identity element in a group G under the binary operation star. If we assume that there are two identity elements in the set G that forms a group under the binary operation star, then these two identity elements must be the same and equal elements as we have shown. And that's the end of the proof of the uniqueness of the identity element of a group. We now prove the uniqueness of the inverse elements of a group. That is, in a group under the binary operation star, every element has an inverse. That is the third property of a group, the existence of inverse elements of a group. And the inverse of each element of a group G, a non-empty set, under the binary operation star is unique. That is, there is exactly one and only one inverse element for each element of the non-empty set G in a group under the binary operation star. And as we did in the proof of the uniqueness of the identity element of a group, to prove that the inverse elements are unique in a group, we will assume that for any arbitrary element of the group, there are two inverse elements for this arbitrary element of the group. And we will show that these two inverse elements are the same and equal inverse element of the arbitrary element of the group. First, we let G be a group under the binary operation star. And we let A be any arbitrary element of the non-empty set G that forms a group under the binary operation star. We let G be a group under star. Because G is a group, then G is a non-empty set, which means it has at least one element. And because G is a group under star here is a binary operation that combines any two elements of the non-empty set G. We let A be any arbitrary element of G. And because G is a group, the elements of G satisfy the third property of a group, which means that each element of G has an inverse. And because A is an element of G, we are sure that A has an inverse. And we denote the inverse of A by A prime. And to show that the inverse of A is unique, we will assume another inverse for A, and we will denote this by A double prime. And to show that there is exactly one inverse for any element A of G, we will show that A prime is equal to A double prime. By the third property of a group, satisfied by the elements of the non-empty set G, A element of G has an inverse. And we let A prime and A double prime be the two inverses of A. Let A prime and A double prime be the two inverse elements of A. And that is a strategy for proving the uniqueness of inverse element. We assume that there are two inverse elements, and we show that these two inverse elements, A prime and A double prime, are the same and equal inverse element of A element of G. Now, by the property of inverse element, if A prime is an inverse of A, then it has the property that if A prime is combined with A by the binary operation star, the result is the identity element E. That is the third property of a group, the existence of inverse element. Similarly, if A double prime is an inverse element of A, if we combine A double prime with the element A by the binary operation star, the result is the identity element E. And now we will show that A prime is equal to A double prime. By the third property of a group, the existence of identity element, E here is the identity element of G. And by the second property of a group, if you combine the identity element with any other element of G by the binary operation star, the result is that element. Thus, A prime is equal to the identity element E combined with A prime by the binary operation star. But the identity element E is equal to A double prime star A. If we combine the inverse A double prime of A by the binary operation star, the result is the identity element. And we use this fact to replace E here with A double prime is star A. So E here now is replaced with A double prime is star A. And we can do that because A double prime star A is equal to the identity element E, because we assume that A double prime is also an inverse of A. Now, to this expression, we apply the associative property. And associative property is one of the properties of a group. And we are sure that this expression is the same and is equal to A double prime star quantity A star A prime. This should be A prime. By associative property, the associative property must be satisfied because we let G be a group under the binary operation star. And associativity is the first property of a group. So by associative property of a group, quantity star A double prime star A prime is equal to A double prime star quantity A star A prime. But A prime is also an inverse element of A. Thus, if we combine A with the inverse element A prime by the binary operation star, the result is the identity element E. Thus, this combination of A and A prime by the binary operation star is equal to the identity element E. Identity element E is equal to A star A prime. So we now replace A star A prime with the identity element E. Because of this property of the inverse element A prime of A. Identity element E is equal to A star A prime. But the identity element has the property that if you combine it with any other element of G, such as A double prime, the inverse element is also an element of G. A double prime star E is equal to A double prime. So this will simplify to A double prime. And we have shown that A prime is equal to A double prime. That means that if A prime and A double prime are two inverse elements of A, element of G, and the inverse element of any element of G is unique, then these two inverse elements A prime and A double prime must be the same and equal elements. And that's what we have shown exactly. We have shown that A prime is equal to A double prime, which means that they are the same element. They are the same inverse element of A. That means that any element of a group cannot have two inverse elements. If there are two inverse elements, then they must be the same and equal inverse elements. And that completes the uniqueness, the proof of the uniqueness of inverse elements of a group. And we denote the end of proof by shaded rectangle. We now define trivial group. Initially, we define group as consisting of a non-empty set G and a binary operation defined on set G. And this non-empty set G, because it is non-empty, should contain at least one element, which means that the minimum number of elements that G can contain to form a group under the binary operation star defined on G is 1. And if G has exactly one element, and G is a group under the binary operation defined on G, we call that group a trivial group. And this one element contained in G for a trivial group must be the identity element. So the trivial group is a group G under the binary operation star, and the non-empty set G consists of exactly one element, and that element is the identity element of the group. The identity element in G under the binary operation star. We define trivial group. A trivial group is a group G under the binary operation star, and G is the set consisting of exactly one element, and that element is E. And we use E to denote the identity element of the group G. So the trivial group is a non-empty set G together with binary operation star, and the set G, the non-empty set G, has exactly one element, and that element is the identity element. Examples of trivial groups: the set consisting of 0 under the binary operation addition is a group. We know that the set of real numbers under the binary operation addition is a group. But if the non-empty set consists of only one element, which is the identity element for addition, which is 0, then the set consisting of 0 under the binary operation star is a group. And this trivial group consisting of 0, the non-empty set consisting of 0 only, and under the binary operations, addition is a group because the three properties of a group are satisfied. If you add 0 to itself 3 times, then obviously the associative property for addition is satisfied. Also, 0 is the identity element for addition, and it is the only element of G. So the identity element for addition 0 is in G. And if you combine this with any other element of G, and because G has no other element except 0, if you combine 0 with 0, the result is 0, the identity element of G. And the inverse element of 0 is minus 0, which simplifies to 0, and 0 is also again in G, which has only one element, 0. So the third property of a group is satisfied. The element 0 of G has an inverse, it is minus 0, but minus 0 is simplifies to 0. So this inverse element minus 0, which is actually 0, is also in G. And the result, when you combine 0 with its inverse, or additive inverse, which is minus 0, is equal to 0, the identity element of G. These are examples of trivial groups. The first trivial group consists of non-empty set G together with binary operation addition, where the non-empty set G has exactly one element, the identity element for addition, which is 0. And I explained this already, why this non-empty set G with only one element, the identity element for addition, under the binary operation addition is a group. Another example of trivial group is this non-empty set G together with the binary operation multiplication, where the non-empty set G has exactly one element and it is 1. 1 is the identity element for multiplication, or 1 is the multiplicative identity for the binary operation multiplication. We know from our earlier examples of groups that the set of real numbers under the binary operation multiplication is a group, because multiplication of real numbers satisfies the associative property. And the second property, there exists an identity element for multiplication of real numbers, which is 1. And 1 has the property that if you multiply 1 by any other real number, the result is the real number. And the third property of a group, the existence of inverse elements. If you consider the set of non-zero real numbers under multiplication is a group. So 0 is not included in this group consisting of non-zero real numbers together with binary operation multiplication. If 0 is not included, then every real number has an inverse or multiplicative inverse, or commonly known as the reciprocal of the real number. And if 0 is not included in the set, because 0 has no multiplicative inverse or reciprocal, because 1 over 0 is not defined or undefined, then the set of non-zero real numbers under the operation multiplication is a group. And this set, non-empty set G consisting of 1 only, the multiplicative identity for multiplication, or the identity element for multiplication, is a group, because obviously the associative property is satisfied if you multiply 1 by itself 3 times. The associative property is satisfied and the result is 1. If you multiply 1 by itself 3 times, regardless of the grouping you use, the result is 1. And the second property, the group contains, the non-empty set G contains the identity element, and the identity element is already in G because 1 is the only element of G. And if you combine 1, the identity element, with any other element of G by the operation multiplication, the result is that other element of G, but G here has no other element because it has exactly one element. If you combine 1 with 1 by multiplication, the result is 1, which is the identity element for multiplication. And the third property, the inverse of 1, the inverse element of 1 of G is 1. The reciprocal of 1 is 1, and 1 is also contained in G. And if we combine 1 with its inverse or multiplicative inverse, 1 times 1 is still 1, and 1 is the identity element in G. Therefore, this group consisting of G with exactly one element, the identity element for multiplication under the binary operation multiplication, is a group. More specifically, this is called a trivial group. Now, we define monoid. We recall that a group consisting of non-empty set under the binary operation star satisfies the three properties: associative property, existence of identity element, and existence of inverse elements. Now, if only the two properties are satisfied, that is the associativity property and the existence of identity element, are the only properties of a group that are satisfied by the non-empty set together with the binary operation on that non-empty set, then we call that set together with binary operation is as a monoid. So a monoid is a algebraic structure consisting of non-empty set together with binary operation that satisfies the associative property and the existence of identity element. We define monoid as an algebraic structure consisting of non-empty set G. Again, G is non-empty set, which means that it has at least one element, together with binary operation star, such that these two properties are satisfied. The first property says that A star quantity B star C is equal to quantity A star B star C for every A, B, C elements of G. And this first property, as we already know, is the associative property of a group. The second property is the existence of identity element of a group. There exists E element of G such that E star A equals A star E equals A for every A element of G. And E here, element of G is called the identity element of G. Example of monoid is the set of positive integers under the operation addition. An example of monoid is the set of integers from 0 to positive infinity. The addition of positive integers satisfies the associative property because 0 and all the positive integers are real numbers, and real numbers satisfy the associative property for addition. And also the set contains the element 0, and 0 is the identity element for addition. and if you add 0 to any other positive integer, the result is the positive integer. But this set consisting of 0 integer and all the positive integers under the binary operation addition is not a group, because the inverse elements of the positive integers, which are negative integers, are not in the set. So the elements of this set consisting of 0 and the positive integers is not a group, because the inverse elements of this set, which are negative integers, are not in the set. But the first two properties are satisfied by this set consisting of 0 and the positive integers. The associative property is satisfied, and the existence of identity element is satisfied because 0 is in the set. So we write one example of monoid is the set of integers 0 and the positive integers under the operation addition. Again, the non-empty set G together with the binary operation addition, where set G consists of the 0 integer and the positive integers, is an example of monoid because the associative property is satisfied. These 0 integer and the positive integers are real numbers, and real numbers satisfy the associative property for addition. The second property of a monoid, the existence of identity element, is also satisfied by G because the identity element for addition is 0 and 0 is contained in G. And 0 has the property that if you add 0 with any other element of G, which are positive integers, or if you combine 0 with itself, the result, if you combine 0 with itself or with any other positive integer by the operation addition, the result is the positive integer. But the third property is of a group is not satisfied because the inverse elements of the positive integers, which are negative integers, are not elements of G. Therefore, G under the operation addition, where G consists of the 0 integer and the positive integers, is not a group but a monoid. Now we define a Abelian group. A group is said to be a commutative group or a Abelian group if the commutative property is satisfied by the elements of the non-empty set G in a group under the binary operation on G. Similarly, a monoid is a group, is commutative or a Abelian if the commutative property is satisfied by the non-empty set in a monoid under the binary operation defined on the non-empty set. But before we formally define a Abelian group or a commutative group, we give another example of a monoid. The set of natural numbers, or the set of counting numbers, or the set of positive integers under the binary operation multiplication is a monoid, because we know that natural numbers or counting numbers are real numbers, and the set of real numbers satisfies the associative property for multiplication. Also, the identity element for multiplication is 1 if you multiply 1 with any other counting number or natural number. The result is the counting number or the natural number. And 1 is the first if you arrange the set of natural numbers in ascending order. 1 is the smallest natural number or counting number, and 1 is contained in the set. So the identity element 1, if you multiply 1 with any other natural number or counting number, the result is the counting number or the natural number, and 1 is contained in the set. But the inverses of the natural numbers, which are the reciprocals of these natural numbers, are not in the set of natural numbers. So the inverses are not in the set. Therefore, the third property, existence of inverse elements, is not satisfied by the set of natural numbers under the operation multiplication. Therefore, the set of natural numbers under the operation multiplication is not a group, but a monoid. But the multiplication of natural numbers or counting numbers satisfies the associative property, satisfies the commutative property for multiplication. We know that because natural numbers or counting numbers or the positive integers are real numbers, and the set of real numbers satisfies the commutative property for multiplication. Therefore, the monoid consisting of the natural numbers under the operation multiplication is commutative or abelian. And the set of natural numbers under the binary operation addition is not a monoid. Although the associative property is satisfied by the set of natural numbers or counting numbers under the operation addition, the identity element 0 is not in the set of natural numbers or counting numbers. Therefore, the set of natural numbers under the binary operation addition is not a monoid. Again, the set of natural numbers denoted by this notation under the binary operation multiplication is an abelian monoid. And the set of natural numbers or the set of counting numbers is actually the set of positive integers. These are the numbers that we use in counting, so they are also known as the counting numbers. And this set together with the operation multiplication is a monoid because multiplication of counting numbers or real numbers satisfies the associative property. And the identity element for multiplication, which is 1 of the natural numbers and is actually the smallest counting number or natural number. And moreover, the set of natural numbers satisfies the commutative property for multiplication, because natural numbers are also real numbers and the set of real numbers satisfies the commutative property for multiplication. Therefore, this monoid is abelian. But as I said earlier, the set of natural numbers or the set of counting numbers under the operation addition is not a monoid because the identity element for addition, which is 0, is not one of the elements, is not one of the counting numbers, is not contained in the set of natural numbers n. But if we take the union of the 0 integer and the natural numbers, we would get our first example of monoid, the monoid consisting of non-empty set G, where G consists of the 0 integer and the positive integers. Under the operation addition is a monoid. Also, that first example of monoid is abelian because addition of real numbers, because the zero and the positive integers are real numbers, and the set of real numbers satisfies the commutative property for addition. Therefore, our first example of monoid earlier is also abelian. Now, abelian is called as such because of Niels Hendrik Abel. He is a mathematician who proved the insolvability of quintic equation. A quintic equation is actually a polynomial equation of degree 5. So, abelian is named after this mathematician, Niels Hendrik Abel, who showed or who proved the insolvability of quintic equation. A quintic equation is a polynomial equation of degree 5, which means that in a quintic equation, the highest exponent of the variable in quintic equation is 5. And it was not only Henrik Abel or Niels Henrik Abel who proved the insolvability of quintic equation. Another mathematician who proved the insolvability of quintic equation is named Galois. And if the commutative property is satisfied by a group consisting of non-empty set G under the binary operation star, then the group is called abelian group or commutative group. We now take some examples of abelian group. An example of abelian group is the set of integers under the operation addition. The set of integers denoted by Z consists of the negative integers, the zero integer, and the positive integers. And the set of integers, because they are real numbers, satisfies the associative property for addition of real numbers. And the identity element 0 for addition is contained in the set of integers Z. Also, the inverse elements are also in Z. The inverse elements of the positive integers are the negative integers, and they are elements of the set of integers. And the inverse elements of the negative integers are the positive integers, and they are also contained in the set of integers. In addition of integers satisfy the commutative property for addition, because the integers are real numbers and the set of integers satisfies the commutative property for addition. Then the set of integers under the operation addition is a commutative group or a abelian group. As I said earlier, the set of integers under the operation addition is a commutative group or abelian group. In addition to the first three properties of a group, associativity, existence of identity element, and existence of inverse elements, the set of integers satisfy the commutative property for addition. Therefore, the set of integers under addition is a group, and it is an abelian group or commutative group. Another example of a commutative group or abelian group is the set Z sub n under the binary operation addition modulo, where the set Z sub n consists of the integers from 0 integer and the positive integers from 1 up to n minus 1. And the operation here is addition modulo n. We take a particular example of this example of abelian group. For n is equal to 4, our set Z sub n, denoted by Z sub 4, will consist of integers from 0 up to n minus 1. Because n is 4 in our example, the last element in Z sub 4 will be 4 minus 1 or 3. Thus, the elements of Z sub 4 are the integers from 0 up to 4 minus 1 or 3. And the binary operation defined on this set Z sub 4 is addition modulo 4. And to show that this is a group, we construct a table. And we said in the lesson before, in one of the lessons before, that if you are given the table, we can easily tell if the set is a group under the given binary operation if each element of the set appears exactly once in any row and in any column of the table. And we will now construct the table for the set Z sub 4 under the binary operation addition modulo 4 to check if this is really a group. And if it's a group, each of these elements must appear exactly once in any row or any column of the table. We combine any two elements of Z sub 4 by addition modulo 4. That is, you add the two elements of C4 and you divide the sum by 4, but the remainder is taken as the answer for the sum of the two elements under addition modulo 4. Example, 0 plus 0 is 0, and if you divide 0 by 4, the remainder is 0, because 0 divided by 4 is 0 and there is no remainder. So 0 plus 0 under addition modulo 4 is 0. The remainder when you divide 0 by 4 is 0. Now we combine 0 and 1. By addition modulo 4, you add 0 and 1. 0 plus 1 is 1. And you divide 1 by 4, the quotient is 0 and the remainder is, the integral quotient is 0 and the remainder is 1. We combine 0 and 2 by addition modulo 4, you add 0 and 2 and you divide 2 by 4. The integral quotient is 0 because we cannot divide 2 by 4 exactly. So the quotient is 0 and the remainder is 2. 0 plus 3 is 3 and we divide the sum 3 by 4. because 3 is not exactly divisible by 4, the integral quotient is 0, and we take 3 as the remainder. We combine 1 by 0. By addition modulo 4, we add 1 plus 0 is 1, and we divide 1 by 4. The remainder, the integral quotient is 0, and the remainder is 1. We add 1 and 1. We add 1 to itself by addition modulo 4. 1 plus 1 is 2, and we divide 2 by 4. The integral quotient is 0, and the remainder is 2. Now, 1 plus 2, we combine 1 and 2 by addition modulo 4. We add 1 and 2. 1 plus 2 is 3, and divide 3 by 4. 3 is not exactly divisible by 4. The integral quotient is 0, and the remainder is 3. Now, we combine 1 and 3 by addition modulo 4. We add 1 and 3. 1 plus 3 is 4, and 4 is exactly divisible by 4. Therefore, there is no remainder. The remainder is 0. We combine 2 and 0 by addition modulo 4. 2 plus 0 is 2, and we divide 2 by 4. 2 is not divisible by 4. So, the integral quotient is 0, and the remainder is 2. 2 plus 1 is 3, and we divide 3 by 4. 3 is not divisible by 4 exactly. So, the integral quotient is 0, and the remainder is 3. We combine 2 and 2 by addition modulo 4. We get the sum 2 and 2. 2 plus 2 is 4, and we divide the sum 4 by 4. 4 is exactly divisible by 4. Therefore, there is no remainder, or the remainder is 0. Now, we combine 2 and 3 by addition modulo 4, but we get the remainder as the result of addition modulo 4. 2 plus 3 is 5. If you divide 5 by 4, the integral quotient is 1, and the remainder is 1. Three plus 0 is 3, and we divide 3 by 4. The remainder is 3. Next, we add 3, and we combine 3 and 1 by addition modulo 4. 3 plus 1 is 4, and 4 is exactly divisible by 4. The integral quotient is 1, and the remainder is 0. We combine 3 and 2 by addition modulo 4. We get the sum 3 and 2. 3 plus 2 is 5, and 5 divided by 4 is, the integral quotient is 1, and the remainder is 1. And 3 plus 3 is 6, and divide 6 by 4, you get 1, and the remainder is 2. You have 3 plus 3 is 6, divide 6 by 4, if you divide 6 by 4, 1, you get 1. 1 multiplied by 4 is 4. And 6 minus 4 is 2. And 2 is the remainder. Therefore, 3 plus 3 Therefore, 3 plus 3 under addition modulo 4 is equal to 2. 2 is the remainder when 3 plus 3 is divided by when 3 plus 3, which is 6, is divided by 4. The remainder is 2. Therefore, 3 plus 3 under addition modulo 4 is 2. Now, by inspection of this table, you can see that each element of the set C4 appears exactly once in any row or in any column. Therefore, the set C4 under addition modulo 4 is a group. Now, how do we check if this group is a commutative group or a Abelian group? Consider the diagonal entries of this matrix or table. If a group is an Abelian group, there should be a symmetry of elements in the table with respect to the diagonal. And the diagonal entries are these entries, and you can see that there is a symmetry of the elements above and below the diagonal. We have 1, 1, 2, 3, and 1. 1, 1, 0, 0, 3, 3 above, and 3, 3 below, 2 and 2, 1 and 1. So this table of entries is symmetric with respect to the diagonal. And if that happens, you are sure that the group is an Abelian group. Therefore, the set C4 under addition modulo 4 is an Abelian group. The set C4 under the binary operation addition modulo 4 is an Abelian group, where the set C4 consists of the integers from 0 to 4 minus 1 or 3. In general, the set of integers C sub n under addition modulo n is an Abelian group, where the set Cn consists of integers from 0 to n minus 1. For your practice, please try the following exercises. Number 1, prove the identity element of this group. The set of integers under the binary operation addition is unique. Number 2, prove the identity element of this is a monoid. The set of natural numbers under the binary operation multiplication is unique. What you will do for numbers 1 and 2 is to assume two identity elements and show, as we have shown in the examples earlier, that these two identity elements are the same and equal identity element. Number 3, show that the set C sub 6 consisting of integers from 0 up to n minus 1, where n is 6, under the binary operation addition modulo 6 is an Abelian group. And for number 3, you have to construct a table and check if each element of C sub 6 appears exactly once in any row or any column of the table, and you conclude that it is a group. And to check if it's an Abelian group, check if there is a symmetry with respect to the diagonal entries of the table. And that completes our lesson today on trivial group, monoid, and Abelian group. If you have questions about the lesson today, please ask your questions in the comments below. Thank you for joining me in my class today in Abstract Algebra.